Now that we've covered the drawing of 2D structures as Lewis structures, Kekulé structures, condensed formulas, and line structures, we're going to talk more about aspects that will help us to picture molecules in three-dimensional space and to know the three-dimensional molecular shape of molecules. This is something that you've also learned in Gen Chem 1. So we start with atomic orbitals, reviewing what the orbital shape is and the size and how size changes as the row of the periodic table changes. An atomic orbital is the region of space around the nucleus. The only orbital available in row 1 of the periodic table is the 1s orbital. But every row of the periodic table adds an s orbital. So there's for row 1, 1s, for row 2, 2s, for row 3, 3s, and so on. And as you move down the rows, the size of the orbital increases. And the 1s orbital is going to be at the center with the 2s orbital surrounding it, and the 3s orbital on the outside of that, and the 4s orbital on the outside of that. These orbitals are spherical, and the space between the orbitals is a node where there is 0% chance of electron density. Electrons can behave like a standing wave. They have upward displacement and downward displacement. And we call that negative and positive character. And in the middle of these two, displacement is the node where there is 0 probability. Beyond the s orbital, the other orbitals that we are primarily concerned with for organic chemistry are the p orbitals. In organic chemistry, our molecules are in row 1, and our atoms that we're considering are typically in row 1 and 2 of the periodic table. They do not have access to d orbitals, and they do not exceed an octet. And so the orbitals we're concerned with are the s orbitals and the p orbitals. The p orbitals are what your Gen Chem book described as dumbbell shape or peanut shape. Row 1 has no p orbitals, just the s orbitals. Row 2 has s and p orbitals. There are 3 p orbitals for each row of the periodic table once p orbitals become available. They are in each their own plane. They're along the x-axis, the y-axis, and the z-axis. They have 2 nodes, or they have 1 node between 2 regions of space, and that is why it is bicolored. It has blue and green because they have the basically one end is positive or upward displacement and the other end is negative or downward displacement. What we can say about that is that they have opposite phases. And if constructive combination would be that the same phase combines, and a destructive combination would be that opposite phases combine. So green to green is fine, but green to blue is destructive. That's weird. Okay. Forming a sigma bond for hydrogen atoms, they have 1s orbitals and only 1s orbitals. And the sigma bond between one hydrogen atom with a second hydrogen atom is formed by combining two s orbitals to form a sigma bond, and we call this end-on overlap. Okay, so we have a graph here, and it's showing that when the atoms are at 0.74, the nucleus are 0.74 angstroms apart, then we are bonded. If the nuclei are further apart than that, then the orbitals are overlapping, and so there's going to be some electron repulsion because the second atom's electrons aren't attracted to the nucleus of the other atom yet. And if they're too far apart, then bond possibility is, as shown on the far right, is not going to occur. Okay, so we say that electrons can behave as waves. When two waves combine, we have A and B, okay? So think of A and B as electrons, and we have a positive phase and a negative phase. So this would be like a p orbital with the blue side being positive and the green side being negative. So we have our p orbital, okay? And p orbitals can form sigma bonds by what we call end-on overlap. But the two orbitals must be in order to form a bond, they must have the same phase. That's called constructive combination. So if two p orbitals form a bond, a sigma bond, then we would have end-on overlap of blue to blue or green to green. And this would be constructive. If you have the opposite, if you have green to blue, overlap, then that is a destructive combination and bonding cannot occur. Okay, how atomic orbitals combine, for as many orbitals as are combining, there are orbitals created. So we create what we call hybrid orbitals. And for the combination of two 1s orbitals, what we form is a sigma or an anti-sigma bonding molecular orbital. So we have our sigma bonding molecular orbital and our sigma anti-bonding molecular orbital. A bond only occurs if there are more bonding orbitals than anti-bonding orbitals. There have to be if there are more electrons in the bonding orbitals than in the anti-bonding orbitals. And for that reason, hydrogen forms a bonding interaction, but helium does not. Because if we have helium here, then in our two 1s orbitals that are combining, I would have a total of 4 electrons. Every orbital can contain 2 electrons, and so our sigma bonding orbital would get 2 electrons, but our sigma anti-bonding orbital would also get 2 electrons. And because the sigma and the sigma star are equal, bonding cannot occur. They cancel each other out. So helium does not form a bond to helium. Other ways that orbitals can combine are to form pi bonds. Pi bonding also involves formation of two new orbitals. If I take one p orbital and I overlap it with a second p orbital, I can form a pi bond provided that they are parallel p orbitals. If we have side-to-side overlap, that is the type of overlap that will result in a pi bond. And so when two p orbitals combine, we get two new orbitals, which are called pi bonding orbital and pi anti-bonding orbital, represented by pi and pi star. As long as only two electrons are going in to forming our pi bond, then we have constructive overlap and our pi bond does exist, which you've already learned that for every pi bond we have two electrons, so that should be familiar to you. Okay, how do our structures look three-dimensionally, and what occurs with orbitals for these structures to exist? So if we have CH4 and we draw the Lewis structure, you end up with the flat, evenly dispersed hydrogens, with all the bonds looking like they're at 90 degrees. But that's not the reality, and that's something that you learned in Gen Chem. What we actually get is that carbon is, in methane, is what we call tetrahedral geometry. And it's going to have bond angles of 109.5, and its electron domain geometry is tetrahedral as well. And we are going to recover what electron domains are, what electron domain geometry is, what molecular geometry is, and what hybrid orbitals are. There are many different ways of representing a structure three-dimensionally. We can represent it in a perspective formula, where a hashed bond is going back in space. So think of it as going back into your computer screen, and a wedge bond is coming out of the computer screen toward you. Let me write out these names. So the dashed bond is called hatch. It's not working. Hatch. And it's going back in the plane. And the solid wedge, we call this a wedge. Well, if it will let me write on it. Is coming out towards you. In three-dimensional space. The ball and stick is a three-dimensional drawing formula. The space-filling formula is harder to look at. And then we have the electrostatic potential map, which is indicating where the dipole moments are and which atoms are the most positive and which atoms are the most negative. Okay, so tetrahedral geometry, if you remember, is an atom that has 4 electron domains, and they must all be bonding electron domains in order for it to be a molecular geometry of tetrahedral. But how do we get this geometry? This geometry is from the sp3 hybrid orbital. And for carbon, what we're doing is we have valence electrons configuration of helium 2s2 to p2. So we have 4 valence electrons, and those electrons are initially at resting state dispersed as 2 electrons in 2s, and 1 electron in possibly 2px and 1 electron in possibly 2py. It could be px, py, or pz that has 1 electron. But only 2 of the p's are going to have 1 electron. So when carbon goes to make a bond, it actually has to distribute one of the s electrons into a p orbital. And so it gets promoted, and then we have 1 electron each in s, p, p, p. And so we have 4 orbitals, each with 1 electron. These orbitals are going to hybridize to form what 4 sp3 orbitals. So we get 4 normal orbitals, 1 s and 3 p's, and they all blend together. Just think about throwing the s and the p and mixing it in a mixer until they all are homogeneous orbitals of equal energy called sp3 orbitals. So we put in 1s plus 3 p's. Hold on, getting my laser pointer. Okay, so we put in 1s and 3 p's, and that is 4 orbitals. These are all blended together until they're equal energy, and those 4 orbitals then make 4 equal orbitals called sp3 orbitals. An sp3 orbital has the characteristic of a small lobe shown in blue and a larger lobe shown in green. Okay, so what they're showing here is that the s and the p orbital is overlapping, and if the s orbital and the interacts with the green side of and they're in phase, then we get a larger green side, and if the s orbital is blue, then we would get a larger blue side. That's not really the important characteristic, but knowing the general shape of an sp3 orbital is important, because these are going to be our bonding orbitals, and the side that has the greatest potential for electron overlap, the green side shown in this particular sp3 orbital, is going to be what we call the bonding orbital, and the blue side would be the anti-bonding side because it has less electron overlap. So the s orbitals add to one lobe of the p, and it subtracts from the other lobe of the p, and we get an sp3 orbital. Okay, so now we have our sp3 orbitals, and these orbitals can form sigma bonds by end-on overlap. So if we have overlap with the large lobe of the sp3 orbital, that will form a sigma bond. When we form a carbon to hydrogen bond, like we do in methane, that is those sigma bonds are formed using an sp3 orbital to an s orbital. So now we're going to start defining our bonds by the orbital types that make them. So our single bonds to hydrogen shown in methane are made from an sp3 orbital to an s orbital, with sp3 being carbon orbital and s being the hydrogen's orbital. So when we have a carbon to carbon sigma bond forming, that bond is described as so for example, we have ethane here. Let's go. Did we talk about electron domains yet? It's just so weird not talking about electron domains, okay? So what we can do is I need to remind you about electron domains. What is an electron domain? Unless I talk about it later. There we go. Never mind. We'll cover that in a minute. Okay. So let's just move forward with what we've already learned. So we have that each of these carbons, when they have 4 bonds, is sp3 bond orbitals. So these are sp3 orbitals bonding to, when they bond to hydrogen, it's an sp3 to s orbital sigma bond. But carbon, since its only orbitals are sp3, when a carbon to carbon bond forms, then that is an sp3 to sp3 sigma bond, as shown here. And this is overlap from the large lobe of the 2 sp3 orbitals bonded to carbon. I want you to notice that they're not showing the small lobe of these sp3 orbitals. We omit those lobes when we draw structures and the orbitals that are forming the bonds. So we have here 2 carbons that are both sp3 hybridized, and they have an sp3 to s bond. And whenever a carbon has sp3 orbitals, then the electron domain geometry is tetrahedral and the molecular geometry is tetrahedral.